Hi, everybody. It's Professor Mitchell. We have finally reached the end of Chapter 8, and that is in Section 8.8 on improper integrals, which sounds kind of naughty and forbidden. Let's see what we're in for here. All right, so you see here two regions. The first region is the region under the curve y equals natural log x over x squared for x greater than 1. So this region extends forever and ever to the right. The question we're going to be asking about a region like this is, even though it has sort of an infinite base, could it possibly have a finite area? And we'll ask the same question about a region like this, the region under the curve y equals 1 over the square root of x for x between 0 and 1. In this case, this region sort of has infinite height because at x equals 0, 1 over the square root of x is undefined. And that's because as x approaches 0 from the right, 1 over the square root of x increases without bound. So despite the fact that this region has infinite height, could it have a finite area? And it turns out in both cases, the answer is yes. Both of these regions have finite area. So let's talk about how to define the type of integral that would give us that area. That is called an improper integral. And there are two different kinds of improper integrals. We call the first one type 1. A type 1 improper integral has one or both of its limits of integration infinite. Either the one limit is infinity, the other limit is negative infinity, or both. So for example, the integral from 0 to infinity of e to the negative x over 2 dx. Let's talk about how we're going to define that. We're first going to talk about the integral from 0 to b of e to the negative x over 2 dx. And then we're going to let b increase without bound. So actually, if you look at the second picture first, it's telling you what the area of that region is. And I'm actually going to fill in some details here in a second. And the claim is that as you let b increase without bound, the total area under that curve is 2. So let's see if we can get ourselves to believe that. All right, here we are. So again, whenever you see an integral like this, and I will give you all the details as soon as we've gone over this problem, you are going to rewrite this as integral from 0 to b of e to the negative x over 2 dx. And then we're going to let b increase without bound. All right, so now in terms of finding an antiderivative for e to the negative x over 2, that's pretty easy. That's just what I call a baby u substitution. It would be e to the negative x over 2 divided by negative 1/2. Okay, now remember this is a limit. Antiderivative is negative 2e to the negative x over 2. We're going to plug in b, plug in 0. And that's going to give us negative 2e to the negative b over 2 minus negative 2e to the 0, right? All right. So that's the expression that they had over on the slide. I'll just rewrite it exactly the way they had it because negative 2e to the 0 is negative 2. So we have negative 2e to the negative b over 2 plus 2, aka 2 minus 2e to the negative b over 2. All right, so now thinking about e to the negative b over 2 as b increases without bound, it may help to think of e to the negative b over 2 as 1 over e to the b over 2. As b increases without bound, e to the b over 2 increases without bound, which means that e to the negative b over 2 is approaching 0. So this limit is in fact equal to 2. All right, and that's how they got what you see here. So the area of the bounded curve is negative 2e to the negative b over 2 plus 2. As you let b increase without bound, that area converges. That's the terminology we're going to be using for that, to 2. All right, so that region with an infinitely long base has a finite area equal to 2. So that's kind of something to wrap your brain around. All right. So let's talk about these type 1 improper integrals. And it's really, I think, simpler than they're making it look here. So because there's letters flying around all over the place here. So there are 3 different situations to consider. The first one is an integral from a number to infinity. That's the kind we were just looking at. The second kind is if your lower limit is negative infinity. So if you have an integral from negative infinity to b of f of x dx, write that as the integral from a to b, and then let a decrease without bound. And then number 3 is sort of a combination of those two things, the integral from negative infinity to infinity. If f of x is continuous on the entire real number line, then what you can do is break that into 2 integrals, the integral from negative infinity to c plus the integral from c to infinity, and then just treat those like in number 1 and number 2. So this integral right here, they talked about in number 2. This integral right here, they talked about in number 1. And all of these will make a lot more sense once we have some actual numbers here. All right. So of course, I have lots of examples for you. In each case, if the limit is finite, we say that the improper integral converges and that the limit is the value of the improper integral. If that limit fails to exist, we say the improper integral diverges. And by the way, we're going to be using those terms converges and diverges all throughout chapter 10. So little sneak peek here for you. All right, this is an important special case, and I was kind of going back and forth. This is one of those situations I haven't talked about in a while. Do I bore you with the proof? Do I skip the proof? And I decided to kind of meet you halfway, all right, in this case. I am not going to work out this entire proof on my tablet, but I am going to kind of talk you through it on here. Let's see, I would sure like to be able to zoom in. I just realized that I have never tried to do that on my Mac before. All right, I just had to do a little homework to figure out how to zoom in on my screen. Okay, so I'm just going to talk you through this rather quickly. We're talking about the integral from 1 to infinity of 1 over x to the p dx. The question is, for what values of p does this integral converge? And when it does converge, what is its value? So first, let's deal with the case where p does not equal 1. Because we're going to use the backwards power rule for that, which does not apply if p equals 1. So in that case, first we'll talk about the integral from 1 to b of 1 over x to the p dx by the backwards power rule. That antiderivative is x to the negative p plus 1 divided by negative p plus 1. Plug in b, plug in 1, and you end up with 1 over 1 minus p times 1 over b to the power p minus 1, subtract 1. So when we take the limit as b increases without bound of that expression, that limit comes out to either 1 over p minus 1 if p is greater than 1, or infinity if p is less than 1. And that's because the limit as b approaches infinity of 1 over b to the power p minus 1 is 0 if p is greater than 1, because in that case, this exponent is positive. However, if p is less than 1, then that limit is infinite. All right, so we have most of the answer to our question. This integral converges to 1 over p minus 1 if p is greater than 1, and it diverges if p is less than 1. So now what about the case where p equals 1? Well, then we're just looking at the integral from 1 to infinity of 1 over x dx, and we know all about that integral. That antiderivative is natural log of x. Plug in b, plug in 1, you get natural log b minus natural log 1. As b increases without bound, that limit is infinity. All right, so the big important takeaway from this is that this integral converges if p is greater than 1. It converges to 1 over p minus 1. If p is less than or equal to 1, it diverges. All right, so now we have a few examples, and we may use that graph somewhere. So let me switch over to the tablet. All right, so this is actually an example of integral 1 over x to the p. And originally I was thinking that I would just use the result that we just talked through. But now I think I'm going to just do it as if we hadn't gone over that to show you an example. Again, these things are always easier to understand with actual numbers here. Okay, so first we have to write this as a limit. So instead of integral 1 to infinity, I'm going to do integral 1 to b. And then instead of 1 over x to the power 1.001, I'm going to write that as x to the power negative 1.001. And then eventually we're going to let b increase without bound. All right, so by the backwards power rule, antiderivative for x to the negative 1.001 is x to the negative 0.001 divided by negative 0.001. And again, we're going to eventually let b increase without bound. All right, so we have, let's see, the limit as b approaches infinity of negative 1 over 0.001 x to the 0.001. Bringing it downstairs because I think that limit will be easier to think about. Minus negative 1 over 0.001 times 1 to the power 0.001. All right, well, as b increases without bound, let's think about what this does. This is a great big gigantic number to the power 0.001. That is still going to increase without bound, all right? Think of that as the 1,000th root of b. Actually, I guess I should, oh, wait a minute. I'm so sorry. I plugged in b, I should have a b there. There we go. Yeah, so think of this as the 1,000th root of b. As b increases without bound, the 1,000th root of b also increases without bound. And since that factor is in the denominator, that's going to take the whole entire expression off to 0. So the value of this limit is 1 over 0.001 times 1 which is 1,000. All right, so this integral converges and its value is 1,000. Kind of an interesting and I think mind-blowing fact, all right, and there's a reason I picked 1.001 here. Referring back to what we were talking about a little while ago, if I replace that 1.001 with a 1 and just talked about the integral from 1 to infinity dx over x, that integral diverges. Its value is infinite. All right, so just by tweaking that exponent just that tiny little bit, it makes the difference between the value is 1,000 and the value is infinite. I remember being kind of blown away by that the first time I heard this. All right, but this is really the end of the problem right here. I don't want to confuse you. Okay, number 2, the integral from 2 to infinity of 1 over x times the square root of x squared minus 1. Okay, so again, we start by writing this as a limit, the limit as b approaches infinity, integral 2 to b. Oh, and you should know when you get ready to do one of these on a quiz or on an exam, I am a bit of a stickler about having you write these properly as limits. Okay, so do write the limit. That's going to be even a bigger issue when we get to the type 2 improper integrals, because it's going to be not even so much tempting to skip it as it is tempting to miss it. All right, so you really have to pay attention. Okay, well, fortunately, we just learned not too long ago about the integral of 1 over x times the square root of x squared minus 1. That antiderivative is the inverse secant of, technically I should say, absolute value x. But then in the very next step, I'm going to drop the absolute value because this whole interval is positive numbers. All right, we're only talking about values of x greater than 2 here. All right, so we can just say the limit as b approaches infinity, inverse secant b minus inverse secant 2. All right, so what does the inverse secant of b do as b increases without bound? Well, I wouldn't blame you if you didn't know the answer right off the top of your head, and so I have drawn a little picture for you. Here is the graph of the function y equals inverse secant of x. So what does y do as x increases without bound? All right, so as x heads off in this direction, we are up on this part of the curve. Y is over here. It is getting closer and closer to pi over 2. All right. Okay, so that limit is pi over 2. And then the inverse secant of 2 is the same as the inverse cosine of 1/2. The inverse cosine of 1/2 is root 3, pi over 3, right? Cosine of pi over 3 is 1/2, which means the secant of pi over 3 is 2. All right. So this integral also converges, and its value is pi over 6, I believe, right? All right. And then the last example. All right. That third scenario we talked about under type 1 improper integrals, the integral from negative infinity to infinity, x over x squared plus 4 to the power 3/2 with respect to x. So the first thing you have to do with these is break them somewhere. Notice that this function that we're integrating is continuous for all values of x because the denominator is never 0. And in fact, the denominator is always positive. Okay. So I'd say at least 9 times out of 10, I usually break them at 0. You don't have to. Okay, so we're going to go integral negative infinity to 0 and then integral 0 to infinity. Okay. So I think what might be helpful here and might save us just a little bit of writing is let's get our antiderivative for x over x squared plus 4 to the 3/2, and then we'll come back to this once we've got that. So I'm going to kind of make this like a sidebar. The indefinite integral of x over x squared plus 4 to the power 3/2 dx. All right, well, might look like a trig sub, but it's actually a lot easier than that, right? This is just a u sub. If we let u equal x squared plus 4, then du is 2x dx. Well, we don't want the 2, we just want x dx. So x dx is going to get replaced with 1/2 du. All right, so this integral becomes 1/2 integral du over u to the 3/2. And by the backwards power rule, that's going to be u to the negative 1/2 divided by negative 1/2, aka times negative 2. Get rid of the 2, and we're left with negative 1 over the square root of u. But this isn't about u. So antiderivative is negative 1 over the square root of x squared plus 4. All right. So now we can pick it up here, and I'm going to rewrite that line on the next slide. So we have integral negative infinity to 0. Oops. X over x squared plus 4 to the 3/2 plus integral 0 to infinity All right, so now those have to be written as limits. So we'll make the first one limit as a approaches negative infinity, integral a to 0. And then we'll write the other one as limit as b approaches infinity, integral 0 to b. Okay, and now maybe you'll see why I wanted to get that antiderivative separately, because now I'm going to put it in here. I would have felt awkward dealing with both of those at the same time. So this is going to be limit as a approaches negative infinity, negative 1 over the square root of x squared plus 4. Remember, that was our antiderivative. Plug in 0, plug in a, plus the limit as b approaches infinity, negative 1 over the square root of x squared plus 4. Plug in b, plug in 0. All right, so we have limit as a approaches negative infinity. When you plug in 0, you get negative 1 over the square root of 4 minus negative 1 over the square root of a squared plus 4 plus Limit as b approaches infinity. Plug in b, you get -1 over the square root of, darn it. Oh no, that's okay, sorry. Second guess myself there for a second. Minus -1 over the square root of 4. All right. As a approaches negative infinity, a squared increases without bound. It's a positive number. So that denominator is going off to infinity, and it's making this term go to 0. And the same thing over here. As b approaches infinity, b squared is also approaching infinity. It's taking the whole denominator off to infinity. It's taking this term to 0. So all you're left with is -1/2 plus 1/2. And the value of this improper integral is actually 0. I hope you don't feel too cheated. I know it's sometimes a letdown when the answer is 0. To some people, not so much to me. All right, so that'll take care of those examples.